Hello, everyone, and welcome to the Bodén Center for Molecular Medicine's Clinical Arena lecture series here at Linköping University. I'm Rosalind Simon, and I'm a senior lecturer here at LIU, and I'm as well as an assistant director of Forum Scientiam, a graduate research school here, and I'll be hosting the arena today. So the central aim of the WCMM arena is to highlight collaborations that bridge researchers from the Faculty of Science and Engineering, Medicine and Health, and the Linköping University Hospital. Today, we're honored to introduce two esteemed Bodén researchers who teamed up in an interest to develop digital methods to assist pathologists in detection and diagnosis. The title of their talk, as you can see, is The Promise of AI in Histopathology, and I'd like to first introduce Anna. Anna is a pathologist, as well as the Vice Director of the Department of Clinical Pathology here at Regions Östergötland. She has experience on a personal and project level in the implementation of digital pathology and clinical routines in collaboration with IT specialists, laboratory professionals, and pathologists. Her research collaboration in digital pathology at LIU include the Department of Biomedical and Clinical Sciences, CMIV, and the IDA Data Hub. Anna is currently working on a thesis evaluating the effects of digital image analysis and digital pathology from the perspective of man-machine interplay and related aspects of clinical implementation. Welcome, Anna. Anna is in collaboration with Jeroen van der Laak, who is an associate professor of computational pathology at the pathology department at Radboud University Medical Center in Nijmegen. Did I say that right? Nijmegen, the Netherlands, as well as a guest professor here at Linköping. He has a background in computer science. He's worked on the application of image analysis for histopathology for over 25 years, and he's currently focusing on the use of deep learning for developing computerized systems to aid in pathology diagnostics. So welcome to you both, and now I'll hand it over to you.
Okay, thanks, Rosalind, for the kind introduction, and thanks for the invitation. Of course, it's a pleasure to be here and to show some of the work that we have done. And also, it's a pleasure. This is the first time that Anna and I present together. So yeah, it's fun to do this together. And we hope to show you different perspectives. So I'm mainly the tech person. So I will cover the AI part. And Anna will show some data and some opinions about the perspective of the pathologist. So this is about AI and histopathology. First, we have to show you some financial disclosures. So these are some of the companies that we work with. But of course, this does not really influence the topic that we discuss today. And maybe briefly to introduce you, this is the team in Linköping that we work with. So see, these are the people from different backgrounds, different perspectives that, well, together form the computational pathology research. So we have a couple of pathologists, we have people from industry, we have academics. And I think it's a nice multidisciplinary team that we have together. Now, maybe very briefly for those who are not completely familiar with pathology. So pathology is, let's say, the art or the science that investigates tissues that are taken from the human body and tries to find whether there is any disease. And if there is a disease, then tries to characterize that disease. And a lot of what we do in pathology is actually based on tissue sections. And what you can see here, maybe most of you have seen this before. What you can see here is this is a paraffin block in which there is some tissue. And then what we typically do in pathology is we use a microtome, which is a device which has a knife, which you can see here in gray. And then we can cut very thin tissue sections that we then can put on a glass slide. And then we apply certain staining procedures to highlight structures in the tissue. And then typically what we do is we investigate the tissue under a microscope. And so a pathologist can, for instance, see whether there is cancer or there is certain diseases. And this is what it would look like under a microscope, for instance. So this is a very well-known staining that's applied a lot in pathology. This is called the HRD staining. And this is what pathologists do on a day-to-day basis. So for every patient where we take tissue, we take biopsies, that the tissue is investigated by a pathologist under a microscope. Now, increasingly, we can replace that microscope by a digital system. So the pathology has been, say, analog optical for a very long time until now, and even still today, most of the world uses microscopes. But what you can see happen now is that, and radiology did this maybe 15, 20 years ago, we are slowly starting to digitize these tissue sections. Now, it has taken a lot of time in pathology, on one hand, because the images that we get are very large, typically larger than they are in radiology. And as a consequence, this really brings quite some additional costs. So pathology is not that fast in digitizing. And well, this is one of the scanners that we use in Nijmegen. It's a different one than is used in Linköping, but there are a couple of these commercially available scanners. And basically, in that scanner, even though it looks very fancy, is mostly a traditional microscope, which is completely automated. And what happens is a glass slide is taken and is just scanned field by field on the microscope, and then these images are stitched together to form one high-resolution image. And as I said, one of the challenges in pathology is that these images, raw data, typically are like 30 gigabytes each, which means a lot of data to deal with. And what we normally do is we store them in image files in a kind of pyramidal multi-resolution structure. And by compressing the images, we can make them a bit more efficient. Now, this is ongoing, and you can see certain countries in the world are quite advanced at this. Linköping was maybe one of the first, even worldwide, that really adopted a full digital workflow. For instance, in the Netherlands, where I am, we also have quite some labs that are fully digitized, but there are also countries where this is really not a reality today and where everything still happens under a microscope. And this is what it would look like for the pathologist. So you can just replace your microscope by a computer screen, and this brings you a lot of workflow improvements. You can easily share images. You can have different views on the image, which is not always possible with a traditional microscope. You can get archival cases more easily. And in this case, as you can see, maybe you could even combine radiology and pathology in certain ways. Now, as I said, Linköping has been very early in this process. And Anna can show you say the process that Linköping went through in the last years to arrive at where they are now.
Yes, so thank you. So this was part to give a local connection to where we are. And the pathology department here in Linköping is employing about 120 staff members, 30 pathologists, including 7 residences. And our production for histopathology cases that we, in terms of digitalizing pathology, mean is about 35,000 cases and 220,000 slides. And now we have done this since 2010 when we started, and step by step, as you can see here in the timeline, we have pushed the limits towards a digital workflow. And this year we will put an end to pathologists in validation or calibration, going from microscopic diagnosis to digital review. And in the end of this month, we will stop turning out the slides and only review them digitally on first hand. We have done a quite long-term collaboration project reviewing the concordance between the modalities, and have found that digital concordance is for 99.1% of the slides. And with that, we find it safe now to turn the slides directly to the archive instead. Since we have practiced this for 10 years, the digital archive is quite large. We have more than 2 million slides in storage, which in storage terms will be 1 petabyte, more than 1 petabyte. And the timeline here, as you can see, is presenting on bottom different projects that we have been engaged in, focusing on development and innovation as well as implementation. And in the middle, there is a summary of different investment in technical equipment, such as scanners and workstations. And on top, in gray, you can see the increasing involvement of pathologists in validation primary diagnostic. In the left corner, you can see the true pioneers, Den Tosterson, the pathologist who started the work in 2010. And there have been a lot of work on system and technical design, investments, scanning and laboratory routine adjustments, integrations with adjacent systems, and also change of diagnostic work routines. And today we are focusing on the next step, the step towards AI tools, supporting different aspects of the diagnostic routine in pathology. And actually we have since 2015 had a machine learning algorithm implemented in the system for nuclear cell counting, specifically used as a pathology assistant for quantifying Ki-67, an immunohistochemistry marker used in breast cancer. And with that, back to Jeroen.
I have to unmute first, of course. Yeah, and it's just one slide that Anna presents, but please realize this is a big effort. I know from the lab in the Netherlands where I am, where I'm working, we are going through the same process, but quite a number of years later. And this is really a big effort. It takes a lot of time and a lot of people involved. So it's not easy to get to this point. And yeah, it's really amazing that we are at this stage now. Now, of course, today's talk is about AI. And with the availability of digital images, so this digitization process, of course, we also get to the point where we have no longer the glass slides, but we have the bits and the bytes. So we can start to apply AI techniques to these images. And this is a kind of a booming field. So here we can see some of the recent publications in this field. And well, it's probably small to read, but a lot of this is about deep learning, which I will explain in a minute, applied to scanned histopathology. And as you can see, quite a lot of these are actually in very high impact journals. Nature Medicine, JAMA. So it's really a booming field. There is a lot of stuff happening there. And what I would like to show you now is one of the studies that we did in Nijmegen. We are also rolling out studies in Linköping, but we are not as advanced in Linköping as we are in my group in Nijmegen. I would like to show you the state of the art for one application, and I would like to show you where I think that we are today. So what is the status of the field and where are we going to move and what is needed to move forward? And I think the research in Linköping will play a very important role there. So this is what it's about. This is one of the publications we did 5 years ago. Deep learning as a tool for increased accuracy and efficiency of histopathological diagnosis. And I think this really captures it very nicely. Now, deep learning, I will not go into a lot of technical detail, but deep learning is all over. If you read magazines or newspapers, a lot of stuff about AI and AI being able to analyze data, analyze images. And a very basic example is shown here. And this is one of the examples that is shown a lot if it's about deep learning. Suppose you would want to train a computer to distinguish between photos of cats and dogs. And this is it's a bit of a silly example, but it's one that for some reason has been used very widely. And let's say with old-fashioned image analysis, we would do this by explicitly programming a computer to find significant features and try to predict which features belong to a cat and which features belong to a dog. So you might look at the nose or the eyes or the ears or whatever. Now, the difference in deep learning is that you don't train the computer explicitly, you just show it many examples, and the computer will pick up the discriminating features itself. So without being explicitly told that this is about cats and dogs, or being explicitly told that the computer should look at, for instance, the shape of the eyes, you just show it to the computer and the computer will learn what is a cat and what is a dog. So it will just pick up these features itself. And the thing that we do, so this is called deep learning, and the thing that we do, the thing in the middle, is called a deep neural network. So this is an artificial neural network that you can train. And now to show you the, let's say, and we know these neural networks are very powerful in analyzing images. And actually, if you have a telephone, probably there is some of this technology in your telephone even. Face recognition, things like that, they rely on these networks. Now, at some point we started to think about how to use this for pathology. And what you can see here is one of the first applications that we studied, and actually is also one that we are still studying in Linköping. This is a lymph node of a breast cancer patient. And the task for the pathologist here would be to see if there is any tumor present in this lymph node. And if there's tumor, then we call it a positive lymph node, and that has that potentially has implications for the treatment of the patient. Now, if you want to do the same trick as that I showed you before, so if you would want to train a computer by showing it, well, let's say positive lymph nodes and negative lymph nodes, and you would have the computer pick up the discriminating features, you would end up with a small problem. And I can show you that in this slide. So this lymph node here is a positive lymph node. It's not easy to see, but actually if we zoom in, then we will find that there is a bit of tumor over there. And maybe if you're a pathologist and you have very sharp sight, then you may have picked this up, but it's not an easy one. Now, if you would use the cat and dog approach to this problem, you have to realize that it's not like a cat and dog photo, a couple of 100 pixels, but this one is actually at the highest resolution, 80,000 by 60,000 pixels. As I showed you in the beginning, this is gigabytes of data. So if you would like to train a computer by showing it examples of positive and negative lymph nodes, you would end up with at least two problems. One is these images are way too large to fit in computer memory. They are extremely large and your computer will just not be able to deal with them. And the second problem would be that different from cats and dogs, where it's quite obvious what is the difference between the two, the difference here between a positive and negative lymph node is as, let's say, as tiny as you can see here in the zoom in. So for a computer to be able to pick up that discriminating feature, you probably would need tens or even hundreds of thousands of images before the computer could find that this is actually what makes the difference. So to be able to deal with histopathological images, what we at some point studied and what was found to be very useful is we try to reduce the problem of histopathology to the more, let's say, to bring it closer to the cat and dog problem by not focusing on the entire image, but by breaking the image into smaller pieces. And so in this case, we delineate the tumor regions. And what we can do now is we can just feed small pieces of this tissue to the network and say, okay, this is tumor metastasis and this is normal lymph node. And by doing that, let's say we reduce the problem in histopathology and we make it much closer to the cat and dog problem, because now it's just finding regions with tumor versus finding regions of normal lymph node, which is actually much easier to do. And here you can see this kind of annotation. Now, this is also one of the pains of this approach. We need people to really make these annotations, which is not always straightforward. Now, the application I would like to show to you today. So I've shown you that deep learning is about training a computer with examples, and we can do this by showing it small image patches. Now, there's one application that we studied a lot, which is about prostate cancer in biopsies. So you probably know that if there is a suspicion that a patient might have prostate cancer, what we do is we take a biopsy, which is a small piece of tissue that we take with a needle from the prostate. And under a microscope, this is what it looks like. So it's a small piece and you can really see the shape of the needle in this. And now the task for the pathologist is twofold. First, the pathologist has to find whether there is cancer. And if there is cancer, then the pathologist will have to assess the aggressiveness of the cancer. Now, we started by studying the first question: can we find cancer automatically with a computer program, with a deep learning model? So what we did was we asked the pathologists, and this is a zoom in of a cancerous region. Now, first we asked the pathologists to delineate these cancerous regions, which you can see here in yellow. And then we train the computer, just like I showed you, by exposing it to cancerous regions and saying this is cancer, and normal prostate and saying this is normal prostate. And if we then apply this model to a new case, which was not used during training, then this would typically be the output. So what you can see is the computer shows in red what it thinks is suspicious for cancer, and in green what it thinks is normal prostate. And here you can see very nicely that the computer is actually quite good at this. It finds the cancer, it recognizes the cancer. And even more than that, you can see that the yellow delineation of the pathologist was not extremely accurate. So the pathologist delineated quite coarsely. And you can see that within the delineation, the computer actually makes a distinction between what is really a cancerous gland and what is stroma, which is basically not directly cancerous. So the computer really picked up the features that define the cancer. Now the next step for the pathologist would be, okay, we found cancer. Now we have to grade the cancer. So we have to attach a label of how aggressive that cancer is. And for that, we normally use the Gleason system, which is shown here. And this Gleason system was developed by a pathologist called Gleason, I think somewhere in the 1960s. And what Gleason did was he had seen many prostate cancers, and he decided that he saw different patterns in these cancers. And what you can see is in the top, what he called pattern 1 is tumor, which resembles normal prostate very much. So it's cancer, but it looks like normal prostate. And then he saw a complete spectrum of different patterns, ultimately arriving at pattern 5 in the bottom, which is most deviant from normal prostate. So that's a very aggressive cancer which doesn't resemble normal prostate at all. And Gleason so distinguished these different patterns, and he decided to give them these scores, these pattern numbers. And this was used in diagnostics in a certain way. So there are guidelines for that. And the way pathologists do this today is they examine the tumor, and then they look at which patterns of these are most prominent in the tumor. So you can have different patterns next to each other. And for instance, if a pathologist would see a tumor which has a pattern 3 and a pattern 4 in it, then the pathologist would look at which of the two patterns is the most prominent. And then the scoring would be a 3 plus 4 if 3 is more dominant, or for instance, 4 plus 3 if the 4 is more dominant. It could also be a 5 plus 3 or a 3 plus 2. So we have multiple scores for that. Now, what we did was, and I will not show you all the details, but what we did was we trained this kind of network, but now not on outputting two classes like tumor, non-tumor, cat and dog. But now we train a network to be able to say, this is a Gleason pattern 3, 4, and 5. I should add pattern 1 and 2 are not scored in biopsies. I don't know the exact background for that, but so typically we score patterns 3, 4, and 5. So we trained a network on, I think, 5 to 10,000 cases that we took from our archives. We used the Gleason scores from the pathology report, and we trained the network to be able to find these tumorous glands, and for every gland make an assessment and say, okay, this looks like pattern 3, 4, 5. And then we can combine that information for an entire biopsy and translate this into a pattern 3 plus 4, which in the meantime, these guidelines are changed every couple of years. So in the meantime, again, there is a new kind of layer on top of that. So this is now called the grade group 1. It's not really that much importance now, but so the computer can really, let's say, do the grading that a pathologist would do. Now, to just give you a couple of examples, this is a prostate biopsy, and here you can really nicely see that the computer found the tumorous regions and assigned a pattern 4 to these regions and a pattern 5 to these regions. And another example, here the computer found some benign glands, so this is just normal prostate, and some Gleason pattern 4. So this is what the computer can do. Now, to be able to value how well the computer does this, we did a study in which we took, I think, some 150 cases. And first we asked 3 very experienced subspecialized pathologists to score these cases. because we needed some kind of a ground truth. We needed a gold standard to compare our algorithm to. And we had these 3 pathologists score these cases. And for the ones that they did not agree on, we had a consensus meeting to see if they could get to an agreement in the second stage. And I think most of the cases were already initially agreed upon, and the ones that were not, I think most of them we reached consensus. Next, we asked 15 pathologists worldwide to score these cases just on H&D section, so the section that I just showed you. And what you can see here is the scores of these pathologists. And here what we did was, for simplicity, we reduced the problem to a 2-class problem. So the benign versus grade groups 1 and 2 are the low risk cases, and grade group 3 to 5 are high risk cases. So what you can see here is an RC curve. So it shows the sensitivity versus the specificity, or 1 minus specificity. And you can see here the scores of the pathologists. And what you can see is that there is quite a difference between pathologists, but you can see they score quite nicely. Now, if we compare the algorithm that we built ourselves to these cases, what you can see is that the algorithm actually is shown here in the dashed orange line. The algorithm is actually quite comparable to the pathologist. So it scores, let's say, as good as a pathologist that signs out these cases on a maybe daily or weekly basis. So the algorithm is as good as a pathologist that you would find in many hospitals. It's not as good as this top-level expert, but yeah, it's comparable to a pathologist. You can also see this from the ROC. The ROC is a measure for how good this test is, and it's an area under the curve of 0.9, which is actually quite good. Now, the next stage in this research was that we wanted to see what happens to the pathologist if we help the pathologist with this algorithm. So the pathologist is helped by the algorithm. Or you could also reverse it and say the algorithm is helped by the pathologist. It's the combination of the pathologist and the algorithm. So what we did was we gave the same 15 pathologists the same cases, the same 150 cases, but after a washout period of, I don't know, a couple of months. And what you can see here is the interface that we used for that. So they got the biopsy, and they got next to that the output of the algorithm. And then the results of that are quite remarkable. You can see it here. What you can see here is a measure for the 15 pathologists. And now this is a weighted kappa value of for every individual pathologist. They're scoring against this ground truth. And what you can see is that there is a whole range of kappa values here. So some do not so good and some do better, but we see a whole range of kappa values. Now, if we look at the same pathologist's kappa value, but now aided by the algorithm, you can see in the green dot that almost all pathologists do better with aid of the algorithm. You can see that the top scoring pathologists are not really helped by the algorithm. They are also not hampered by it. They don't suffer from it, but they also are not really, they don't score any better than they already did. But you can see that most of the pathologists actually do much better with the help of the algorithm. And if we look at the same data in a box plot, what you can nicely see is the left one is without computer aid and the right one is with computer aid. You can see that on one hand, the average score or the median score goes up significantly, but also you can see that the range of values goes down. So it's a narrower range, which means that pathologists score better and score more consistently by aid of the algorithm, which is, of course, is a great message because it shows the potential of computer-aided diagnostics. Now, in the meantime, we also we organized a grand challenge in which we asked researchers worldwide to try and work on this problem. And what we found was that, it's a very busy graph, I realize that, but what we found was that algorithms that were trained on cases from Sweden and the Netherlands, which are shown in pink, if we apply these algorithms to cases from the US, which is the blue-purple bar, I think, you can see that the algorithms do a bit less, but still they score very high. They still score kappas of 0.9. So what it shows is that these algorithms also translate very nicely to completely unseen cases. These are trained on European cases and then used for cases from the US, completely different labs, completely different situation, and still they perform remarkably well. So the question then is, does it mean this problem is solved? Should we just bring in the algorithm in any pathology lab, or even worse, should we just replace every pathologist by an algorithm? Now, I think that, and this is one example of a study that we did, but we see a lot of these reports, a lot of publications that say, okay, we tested this, mostly in the setup similar to what we did. And then the conclusion is always, okay, we can beat pathologists. We are as good as pathologists or even better than pathologists. Now, I would argue that it's not really a fair comparison. And the reason for that I can show you here. You have to realize that what we do in these studies is we bring back the pathology diagnostics to a very simple, narrow task, which is not really representative of what a pathologist is doing. Because a pathologist would never look at one tissue section like we did in this Gleason study. A pathologist always has multiple sections for one case. Not always, but in most cases. So a pathologist never has to do this on one single section. It means that if a pathologist would miss a cancer or underscore something, there would always be more sections. So it means that by reducing this to one single section in the study setup, we are really limiting the problem so much that it's not representative for what a pathologist does in the daily work. And also the type of mistake a pathologist would make in a daily routine would not be so severe as in the study setting. Another option that a pathologist has in daily practice, which is not mirrored in these studies, is that a pathologist, if they are unsure, they can ask for recuts of the tissue block. They can ask for, let's say, deeper cuts to get more information. Another option that we do not give in study settings, which is used on a daily basis by pathologists, is they can ask for special stainings if they doubt. And of course, a very relevant thing that is not included in the studies is if a pathologist doubts, they can always ask a colleague. So by reducing the problem to a very narrow task, we are biasing the score of the pathologists. Now, this is a study in which they discuss the same thing. Here they say, because we limit in our studies, let's say, to one single task, here it's stated that basically what we should aim for in our AI is to go for 100% sensitivity, 100% specificity. Now, I think that's also not fair because no test is perfect. And I think the truth is in the middle. So I think we should start doing randomized controlled trials. We should really start to study these algorithms in a real world setting to see how they perform and really perform in true practice. Now, to show you a bit where I think we are now and where we should go, I think what we would need in the future is we will need even more data. Data is key in all kinds of AI. So we need more data. And we have, as I said, we have to start validating our algorithms in routine practice. I think that's a very critical component of what we have to do in the future. One very important point is, even if we can build these algorithms, we have to talk to the regulators because we have to know when is it safe to use an algorithm? What do we have to do before we can start using algorithms on real patient data? We have to study usability. Even if we have a great algorithm, what is the best way of bringing that to the pathologist? And there are two topics that are really not that studied that much yet, which is ethics. Of course, bringing in AI, it's been discussed a lot, also brings ethical questions. Who is responsible? How do you deal with data? And this is about explainable AI. We also have to think about if a pathologist is going to use AI, what can we do to make the pathologist feel secure and make the pathologist understand what the AI is exactly doing? Now, some of these topics will be addressed in a project that we just started, the Big Picture project. It's a very large project, which is coordinated from my group in Nijmegen. And actually, Linköping plays a very important role in this project as well. Anna is one of the work package leaders in this project, and also CMIV plays an important role. And in this project, and I will not go into a lot of detail because we only started 3 weeks ago. In this project, what we aim to do is we aim to build work package 2 is about infrastructure. So we will set up a very large infrastructure to host these images and their clinical data. And we aim for hosting 3 million slides with a specific aim of building and validating AI tools. Now, work package 3 is the one that Anna is involved. That's about collecting the data. So it has a lot of pathologists, pathology labs, but also pharmaceutical companies. And we will try to populate the infrastructure with 3 million cases. And then workbench 4, we will work on AI models. And workbench 5, which is a very important one, we'll also look at the ethical, regulatory aspects, legal aspects of being able to share slides using AI. So very important as well. Well, that brings me to the end of my part. And Anna will take over now and share some of her insights in, let's say, how the pathologist feels about the promise of AI.
Yes, thank you. So this is more, I think the expectations from us, the pathologists, are more on terms of a companion, a diagnostic companion on specific task facilitators, such as helping the pathologist being more effective and also more specific in the diagnostic review, either from an attention-driven approach or in search for differential diagnosis. It would also be nice to have a task helper applied to tasks that is performed repetitively, like measuring size, looking for margins, etc. If a probability model, like Jeroen showed in heat map, performed by AI is the result, it should also be presented as a summary to overcome manual documentation. And other expectations are on maybe more of a management information level, such as prioritizing cases and maybe supporting predetermined protocols for ancillary testings, or being a quality assurance tool to support internal quality control of a diagnosis, such as different grades of basal cell carcinoma. So the first step is maybe not to be replaced, but to have this assistant. There are diagnostic challenges. If I can have the next slide, please. Pathology is a quantitative discipline, like Jeroen tried to explain, and seldom diagnoses are based on one single task. Many of the criteria to the diagnosis and cellular changes are based on language description and of findings, and typical images support the definition. And as most medical practice, pathology is based on a subjectivity interpreted by the practitioner, the pathologist, from learning models that is transferred from other pathologists and also literature. The protocols that we use today when we practice the diagnostic review are built on today man-made visual concepts, also based from microscopic review. And it's not always so easy to transform them into an algorithm with robustness for laboratory and morphological variability. New heart prediction and prognostic models from unsupervised learning lack evidence from randomized clinical trials, and therefore it is hard to justify them in clinical practice today. And how to apply an algorithm may present as an elementary problem, but getting access to good computer force in line with your clinical system and solving the best application strategy is not yet solved routinely. Comparing to ancillary testing, it is applicable on block and slide level, but with AI, there are multiple possible application levels. Most of all, AI is also a medical technical device, and as Jeroen said, there's quite a lot of regulatory issues that needs to be solved. And the application in clinical system of well-performing algorithm from controlled data sets often shown a decline in performance, even though you had good results, and of course depending on set thresholds. AI nevertheless tends to give a lot of predictions that needs to be handled and labeled, and this is time consuming as it appears today. And the next slide. And also there are implementation challenges of various issues such as legal and technical standards and lack of local expertise, how to validate, calibrate, and monitor results produced by AI over time. Here is a need of collaboration with medicine and engineering with emphasis on IT and image analysis, as pathologists is not the right educated persons for this task, even though we depend and will work with the result. AI models are transferred from black boxes, but can and must be explainable between the disciplines. And another problem is that AI models tend to inherit limitations in model performance and generalizability. Lastly, the promise of AI in histopathology is that we have this really cool AI stuff that we want to implement. But nothing is free of charge, and there are investments and time efforts presumably adding on top of demand for healthcare today. And we know there's an economic crisis here also. Therefore, it is important to, as along while we're trying to put this into clinic, also compare it to golden standards, but with a wider perspective of patients and health economic. And then I think we have the last slide, and this presents some of the logos from sponsors in different projects supporting AI development driven from Radboud University Medical Center and Linköping University, and of course Region Östergötland. And I think thank you for your attention. And with that, I think we have 4 minutes left for Jeroen and questions.
Yeah, so I'd like to turn it over. Thank you for that excellent presentation. That was just really clear and really nice.